Well, let's go into materials. So, your work over the last few years has been in automating materials discovery. On your LinkedIn, I saw you talk about through the use of SolidWorks, 3D modeling and printing and microcontrollers, I'm developing equipment for specific laboratory tasks that will be used together with robotic solutions to automate all of the scientists' artisanal work. I love that term, artisanal work. Maybe gets back to the woodworking sort of story. So not being a material science myself, and I know you are not either, so maybe we'll learn together here, but I was trying to think of how might I simplify this so that I understand the process of coming up with a new material. And so the kind of example that I'd like to offer is, let's say that I work for a large airplane engine manufacturer like General Electric, GE. I know that they, when I'm flying from California back home on the East Coast, right? I'm flying in these Boeing planes. They've got a GE engine strapped to them, or hopefully more than one, a couple. Yeah. And I'm thinking, okay, well, I know that, airplanes use a lot of fuel, so it'd be helpful for them to be lighter, and that will help them use less fuel, which is good for their bottom line, also good for the environment. And so let's say that I'm at GE and I want to create some new alloy or metal for the turbines in that engine. So the steps that I might go through, first I might define the requirements for that metal. And so that might be things like, what is the tensile strength that I need for these turbines? What is their resistance to different temperature fluctuations, to corrosion when they're sitting out and it's hailing or sleeting outside? I then, as a next step, might then take an educated guess based off of my experience as a material scientist, based off of research that I might see around what are some of the different, essentially, metals. So essentially elements that I can combine from the periodic table to create certain types of metals that might have those kinds of properties. What I as I understand it, ultimately those are formed into crystals, lattices, and grains. Those are kind of the elemental structures of metals. So what might create lattices, grains, and structures of that sort that have those properties? The next step is I might then try to make that material. So I think in the material science world it's called synthesis.
Yes.
And it involves processes like heating, applying pressure, cooling those kinds of metals, or those substances to create that alloy. Then I want to test to make sure that what I actually created was what I wanted to create. So that's what we get into this process of characterization.
Yes.
And it sounds like one popular way is like X-ray diffraction or
XRD.
XRD, okay. And so once I've done some X-ray diffraction, I might then go into performance testing, which is saying, okay, I've made what I think I wanted to make. Now let's actually put it in an environment and apply these kinds of performance criteria. And if it's successful, awesome. If not, which is probably going to be the case at least the first few times,
yes,
I go back to the drawing board and continue to test new hypotheses. So that's kind of like 5 steps to go from sort of a certain requirement to the potential thing that I've created.
Yes.
Does that feel broad picture like the right story?
Yes, it feels correct based on what I see from my coworkers here. They do all this amazing work.
Okay, cool. So as I reflect on that process, like one big challenge that I see in that process is in step 2, right? Taking that educated guess of, what are the materials that I want to create that are going to have these performance requirements. There's an infinite number of ways in which I can combine these different elements from the periodic table. And, I'm not really sure where to start. So one initiative that I have seen, at least described, is the Materials Project, which is this open source database where you have known and predicted properties of 170,000 materials that the Berkeley National Lab as well as other organizations have been creating. And then further, there was a collaboration with DeepMind for their graph networks for materials exploration, which added some 380,000 more stable materials into that database. So my sense is one innovation from the kind of material science end is being able to make this database accessible with these predicted quantities to facilitate that educated guess step of the process. Am I understanding that correctly?
No, it's perfect. Yeah.
Okay. I know this isn't your specific domain, but anything that you would elaborate or add to that sort of like the novelty or the importance of having that kind of a database?
So people on the material science side, when they are investigating a material, they work a lot with the simulations, right? So this database would provide a lot of information on, sometimes you want to simulate that material in a certain condition, right? So you want to kind of test some properties. So what I see people here doing many times is they use the material as a base to try to see a possibility of what else they can do, maybe adding something or removing something. And this is what they do here. Like the theory side people, the theorists, they invest a lot of time, looking at these crystal structures. And I find amazing because I know nothing what's going on. I just see them, staring at the screen, rotating this crystal, and literally just pondering. You see them, they're not writing anything, they just ponder. So their minds can work, with the structure that is being simulated and get a lot of information from that. It's really cool how, how deep we got into this field of science where, and when I see them discussing about the materials, they know, how to phrase a sentence about changing specific one side of the structure to something, and then like everyone just agrees, oh yeah, that's right, and then I'm like, well, that's really cool, right? I have no idea, but I like that. So it's very impressive on how they do this, first initial screening. They do simulations, they get energy levels, they get all of these properties, just analyzing, virtual data. And then many times it's just like, okay, this material is exactly what we need, but can we make it? And then that's when the job goes from the experimental side, from the theory side to the experimental side, where people are going to try to find a recipe to get there. So the A-Lab, for example, is a lab that helps on this process to transition from the theory to the application side.
That's fascinating. As I'm imagining folks looking at these structures and trying to see what they might add into those structures, that almost feels like art in a way, or some sort of magical, experience. But I imagine there's a lot of, again, personal experience and maybe pattern recognition that they're drawing from that allows them to get that intuition for where to go.
That's right. That's how I believe it works in their brains. They have their own materials project in their mind, where they consult like, oh, I think we can try this. That's how I picture that they think. Because literally, I saw this many times. They stare at the screen, they rotate the crystal, and they're just like ponder. It's very interesting. That's not how I saw people work in other scientific fields before, when I was working with the wood science people.
The other thing that strikes me in that is, I think as a sort of a layperson entering this field, my sense is, well, if you can come up with some properties for material that you would want to make, of course you can just make it, right? Like we could make anything. It turns out that's not true. And I think the second layer of that, which I'm starting to learn, is that even for the things that we can make, if it requires some exotic, materials that are not easily accessible or accessible at scale, it almost doesn't matter that we can make it, because if you're trying to create, new blades for jet engines, you're going to need a lot of that material. That's and right. If it's super expensive or, not available in, areas that we have access to, then that's a non-starter as well, which adds, again, another layer of complexity. Mm-hmm. Cool. So, okay, so there's the sort of understanding and having an intuition for where we might want to, what ingredients we might want to assemble. Then there is the synthesis part of it, right? So making the materials, and it's time-consuming, involves a lot of trial and error, and it seems like that's where the magic of your lab really shines, is in that
right.
synthesis. So I'm curious, could you maybe share a bit more about what synthesis looks like in your lab, and what was your innovation or breakthrough here, and how that happens?
So the A lab is an autonomous lab that would work specifically with the high temperature synthesis. So because what we are working here is for energy storage, and these reactions, they happen in what we call solid state. So we just mix powders and then we bake them, you know. And then all the calculations that the people do on the simulation side is to be sure that when the atoms react, they would go where we need them to go. So, you know, but that's the hope, that nature is going to do what we want nature to do, right? That's not of course, what happens many times. So then changing parameters like the ramping curve the ramp curve of the heat, plus the time you keep on that temperature, the way you cool it down, and you know, all of these are parameters that change how this material is going to behave. So one thing I learned that I found fascinating is the lab is not capable of doing that right now because of the safety of the robots. But when people are doing in the lab, they have these big tongs that they go and they take the crucible from the furnace, and like from 1,000 Celsius, they cool it down very quickly, because then the materials, when they cool down quickly, they tend to hold the properties that they had when they were in that high temperature. So no, there are these like secrets that the experimentalists have on the way they manufacture materials that try to hold the temperature. So the lab is very limited in many ways because we don't have the flexibility of a human doing things. But the lab would work 24/7 on the field that it can work, and that's where it helps a lot. So, but all of the reactions are exactly in this idea, like the high temperature synthesis, and then it goes from, we provide the material, we provide the target, the artificial intelligence models are going to look for similar structures that were manufactured this or that way. Then it's going to create an initial recipe on the like ramp curve of the heat, and you know, all these parameters. Then the powder station, the powder dosing is going to dose all these powders, mix them, then go to the furnace. Then the furnaces are automated. And the first part of my work here was to automate the doors of the furnaces, because we already had them. So there are some companies that make furnaces that their doors open automatically. But my first job here, because we already had the furnaces, was to automate them. So then what I did was just to use an Arduino and how do you call that one? Linear actuator, to open and close the door. So I had sensors here and there, that was my first job, to automate the furnaces. And then because the communication with the furnace was already there, we could remotely control the temperature and monitor. But opening and closing and putting samples inside, this is not part of the companies, at least at that time, were looking. I hope that now they are looking for equipment that is exactly considering the need of this integration between robots and humans, that would help on that sense. So, well, that's basically what the lab does. And then on the synthesis. But then we have the characterization. So the lab only performs XRD and basically takes these powders that sometimes would become a hard material, and then for the XRD they need to be in the powder form. So then we grind them, and then we place them on the disks, and then from the disks they go to the XRD machine. Then the data from the machine goes to the computer compares the data that's also obtained from the expected data, and then makes a decision on yes, I made it, no, I didn't. So what I can try here based on previous data. Wow. So that's the decision on the next recipe comes from this input, and then keeps going.
Wow. So it's really moving towards closing that loop and having that, autonomous cycle that you're describing.
Yes.
Yeah. Wow. So you said a couple of things that struck me. One is, you mentioned your North Star here, your mission really is around energy and identifying kind of maybe new materials for energy storage. So to put it maybe in layman's terms, right? We all have lithium-ion batteries, right, in our phones, and I think EV cars use them as well. Are these the kind of sort of energy storage solutions that you guys are looking at?
No, we are moving away from that. So lithium has amazing properties in many senses, and I don't think the lithium batteries are going to disappear, next year. But we should move away because lithium is, flammable in air, and we have many cases of like batteries being on fire. It's a fire hazard, and I even know that in auto shops now, some of them are required to have like a place to, like, if the car is on fire, they put the whole car under the water.
Wow.
That's a safety precaution that it's being implemented because of the hazards, right? The batteries, they have a lot of energy. If this energy comes out quickly, too quickly, then it will be a problem. So what we have now that it's not probably, but I'm pretty sure this will be the next standard on batteries, are the disordered rock salt. Disordered rock salt is this material that is stable in air and it doesn't catch fire. And I think the biggest advantage, but don't quote me on that because I'm not a material scientist, but the feeling I have about this material is that it has no liquids inside. So electrolytes are not necessary to make the material work like in lithium batteries. So just by removing the electrolyte, this liquid part, the battery becomes way lighter. So then you have what is very important for any transportation modality, that is the energy density. So these new materials that we are looking for today, they should be more stable, less hazards in many senses, more sustainable, but also with more energy density.
I imagine energy density is especially important for new applications if you want to do, for example, electric powered flight, where you get into this cycle, right, which is the larger the battery, the heavier the plane, the more power required to carry said battery, and so on and so forth. Lighter batteries will really help with that.
Yes.
And then safety being the other big aspect as well that you mentioned. Okay. I'm curious, so you mentioned there's this, you make the materials, you synthesize them, and then you characterize them with, XRD, make sure that we've made what we wanted to make. Is there a point in the process where and maybe this, again, I'm not thinking about this right, but where you see, okay, how much of a charge can this material hold? Like, what is the actual energy density of this, or does that happen at a later step?
So I think everything starts on the theory side still, because they know from the simulations how much energy can be stored in that material.
Oh, wow.
Yeah. So this is why they know that pursuing this, maybe not this material specifically, but this field of materials, all of them here will have similar properties, then that's how they know before even starting that that's a good shot to try.
Oh, wow. Okay.
So, and then later they have to test the material, because what we make in real life is not exactly how the perfect realm of the simulation, right? Where the material is perfect, there's nothing wrong with it, no gaps, no contaminations, but they intend to happen in real life. So then after manufacturing the material, they're going to test this material on cycles, usually since it's a battery, right? So they do the full charge and discharge cycles, and then they get the real information about the material that they could make and how close they are to the theoretical material.